Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's start. It's a great pleasure to introduce Bruce Kleiner from University of Michigan. And he'll talk about Perelman's work on the geometrization conjecture. This is the first of a series of 3 talks. There's going to be another one on Thursday and another one on Friday. Thanks.
Thank you. Thanks for the invitation to come here and speak about this stuff. So, I should begin by saying that Perelman's work and the earlier work by Hamilton, on which it's based, is really a long story, and there's no way that I could cover it in any detail in 3 lectures, even if it were to an audience of specialists, which I'm not assuming. So my purpose is really to, give some background first, and then try to sketch in some of the ideas that go into Perelman's argument. And I hope that that along the way you'll get some idea of really how it's supposed to work and why it might be plausible that such a program can actually be made to work. But given the constraints, I don't think it would make sense to try to do too much more than that. Okay, so I'm going to try to make this as accessible as I can. But it may be that I've kind of misjudged the audience or something. If you have any questions at any time, feel free to interject. Okay, so this is really a theorem. Actually, could someone kill the lights in the front to diminish the shadow? They've probably gone out for their coffee already. There we go. Thank you. Okay, so this is really it's going to be a theorem about topology, but phrased in the language of geometry, proved using methods from analysis. But let's start the story with topology. So let's start with surfaces. Maybe I can zoom this. Is that legible? Okay. So I guess everybody knows if you have a closed connected surface M, then you can write it as a connected sum. So M is this connected sum of N1 through Nk, where each of these Ni's are either 2 spheres, projective planes, or tori. Okay? Let me remind you that the connected sum of 2 manifolds, and this works in any dimension, is really given by the following picture. You have a manifold here. Let's call it, say, N1, and another manifold here, schematically like this, N2. And to perform the connected sum, you identify a ball topologically in one of them, or a diffeomorphic copy of a ball, and a ball in the other, and then you remove the interior of the ball from both of them. So I'm removing this part, and then I remove that part. And having done that, I now have 2 manifolds with spherical boundary. Okay? So they have spherical boundary components, and then I can glue them together. So if these manifolds happen to have orientations, then you want to choose the gluing in a way that respects the orientation. Okay, but I'll generally be sloppy about that kind of thing. That's just a reminder of what the connected sum is. And so this is the assertion. So this is very nice. It says that all surfaces can be built up with a very short list of building blocks. Okay. Well, what about surfaces from a geometric viewpoint? Well, so here's an assertion. So this was known in the 19th century. So if you take a closed connected surface M, and that admits a Riemannian metric, G sub M, with constant Gaussian curvature. And after scaling, you can assume the curvature is either 1, 0, or -1. All right, so what does it mean to have a metric with constant curvature? Well, one thing it means is that given any 2 points in the surface, okay, then you can find a neighborhood of one and a neighborhood of the other, which are isometric. Okay? Now, the size of those neighborhoods may depend upon where the points are, but on a sufficiently small scale, the object looks the same near one point as it looks near the other. So it's, the term that's usually used for this is that it's locally homogeneous. Okay? And, well, so the sign of the curvature is a topological invariant. It's the same as the sign of the Euler characteristic, and that follows from the Gaspone theorem, which says that up to a normalizing factor, the Euler characteristic is the integral of the curvature. Okay, so examples of this. Well, to get a metric of constant curvature on the two-sphere, you just take the usual model for the two-sphere, and that metric has constant curvature 1. To get a metric on the projective plane, well, you think of it in the usual way. You take the two-sphere and you identify antipodal pairs, okay? And the Riemannian metric descends to that quotient. Well, to get a flat metric on a torus, well, you can think of taking the unit square and then gluing the opposite sides in the usual fashion to obtain the flat metric there. Or you can think of it as a quotient of the plane, R2, where you mod out by integer translations. So z squared is the lattice of integer translations. So if you look at the universal covering map here from M tilde, universal cover, well, then you can use this map to pull back the geometry, or pull back the metric to M tilde. And so this now gives you a metric on the universal cover, which is simply connected because...
We have to bring the lights back here because it's too dark for the cameras.
Okay. Well... maybe I can drape a sheet over this or something. This doesn't look that bad, does it? Yeah. Okay, so, right, so then if you look at the pullback metric, so the universal cover is diffeomorphic to R2, okay? But that pullback metric has now constant curvature, and it's simply connected. So a classical theorem says that after you unwrap it, then there's essentially only one model with a given curvature. Okay? Once you know the curvature, then it's isometric to a model space. It's either the round two-sphere if the curvature is 1, the Euclidean plane if the curvature is 0, or the hyperbolic plane if the curvature is -1. Okay? So once you unwrap things, then you get a very short list. Okay, so so now let's pass to three manifolds. So we could naively hope for a similar story when dealing with three manifolds. So I'm going to assume that all three manifolds are orientable henceforth, without saying it. I mean, essentially everything can be adapted to the general case, but it makes things a little bit more cluttered. Okay, so I'll say the three manifold is prime if it's non-trivial, which means it's not diffeomorphic to the three-sphere. Maybe I can turn the light up here. Does anyone know how to increase the brightness of the light here? Oh. If I press light, the light's probably going to go off. So anyway. So it should be non-trivial, not diffeomorphic to a three-sphere. And it shouldn't be decomposable into a connected sum in a non-trivial way. So where neither of the sum ends is non-trivial. Okay, so this is analogous to the notion of a prime number, right? Except the semigroup operation is connected sum instead of multiplication. Okay, so well, now there's a theorem. It's like the prime factorization theorem for integers, says that every closed connected orientable non-trivial three manifold can be decomposed as a connected sum of prime manifolds. Okay, so you can write it as a connected sum, and what's interesting here is actually the prime factors are uniquely determined by the original manifold up to indexing. Okay, so think back to the first slide when we were talking about surfaces. So this says that any three manifold can be written as a connected sum of prime pieces. Okay, so this makes you ask, well, what are the prime pieces? Okay, well, So what are the prime pieces? What are some examples of prime manifolds? Well, obvious example would be projective 3 space. Okay? But more generally, you can use lens spaces. So there's a class of examples of prime 3 manifolds which are all, in some sense, analogous to the projective plane. And you can think of them uniformly in the following way. So you can take a finite group of orthogonal transformations. Let's call it capital gamma. So this is a set of orthogonal transformations in R4, or rotations, if you like. And you let this group gamma act on the unit 3 sphere sitting in R4, and you form the quotient. Okay? So these are spherical space forms. Well, you can look at more general space forms. You can do the same kind of thing, where starting with an X, which is one of these model spaces, the round 3 sphere, flat 3 space, or hyperbolic 3 space. Okay? So you take a discrete group of isometries gamma, which you assume acts freely on X, and then you form the quotient. Okay? If you choose gamma correctly, you'll get a nice compact manifold, and that will be prime. So some examples. Well, the 3 torus. So there are also a number of examples which have finite covers, which are diffeomorphic to the 3 torus, but which are not themselves a 3 torus. What about hyperbolic examples? Well, these are a little bit harder to come by. The simplest ones to think of are the following. So you can build a hyperbolic space form by taking a regular hyperbolic dodecahedron. So in hyperbolic 3 space, you can take a dodecahedron, which is regular, so all the faces are isometric to one another. All angles are the same, et cetera. But where the dihedral angles are adjusted to be 2 pi over 5, and then if you glue the faces in pairs in the appropriate way, what you'll get is an object which is really a closed 3-manifold, okay? Which has a hyperbolic metric. All right, so these are some examples of prime manifolds. But that's not all. Okay, so far we've seen examples which are in an obvious way analogous to the examples from surfaces. Well, you can make things more general by looking at more general model spaces. So instead of looking at just the round 3 sphere, flat 3 space, and hyperbolic 3 space, you can look at more complicated but still homogeneous model spaces. Okay, example, take the 2 sphere across R, or take the hyperbolic plane across R. And there are other examples of homogeneous spaces. So there are 2 3-dimensional Lie groups which come in here, or sorry, 3 rather. So SL2R, or SL2R tilde, so if you take the group of 2 by 2 matrices with determinant 1, that Lie group, you look at the universal cover. So to think of this as a geometry, so that's a nice Lie group, but then since it's a group, you have a natural group of diffeomorphisms acting. Namely, you can think of the group acting on itself by left translations. Okay? So it makes sense to talk about Riemannian metric with respect to which each left translation is an isometry. Okay? So this is called a left invariant Riemannian metric. So if you put a suitable left invariant Riemannian metric on each of these 3 3-dimensional Lie groups, then you get a nice space form, and you can produce a number of more examples, some additional examples of prime 3 manifolds by dividing out by subgroups of the isometry group. Okay? So, question? I'm not sure what language you prefer to hear this in, but one way of thinking about it is you can think of this as a semi-direct product of R2 with R. Okay? So it's a 3-dimensional Lie group. It's diffeomorphic to R, if you like. It has a normal subgroup, which is just R2, so that abelian group. Okay? And this R, if you look at how the R acts on this by conjugation, it acts by a diagonal matrix. So you can think of it as sort of expanding exponentially in one direction and contracting exponentially by the opposite way. Okay. And nil is just the group of 3 by 3 upper triangular matrices. OK, so these are simply connected homogeneous Riemannian manifolds. So these, together with the constant curvature spaces we had before, are called Thurston geometries. OK, so we have 8 Thurston geometries floating around here. And as I said a moment ago, you can get more prime manifolds by using the same construction. We take X to be one of these guys, and then we mod out by an appropriately chosen group of isometries.
Bruce, can you say something in 10 words or less about why they're all prime? It's a little surprising considering that that's not the case in 2 dimensions. Quotients of hyperbolic space are not.
Well, the point is that, essentially to test primeness, what you want to do is to say, suppose you have an embedded 2-sphere sitting in your manifold. You'd like to know that on one side or the other you have a 3-ball. Okay, this is essentially what it boils down to, not quite. But since the 2-sphere is simply connected, if you now look at the universal covering, well, then you can lift that 2-sphere to the universal cover. Okay? Now, if you drop down 1 dimension, the 2-sphere would become a circle, and you couldn't lift it. Okay? So once you lift the 2-sphere to the universal cover is just a copy of R3. And you see a 2-sphere sitting there. Well, by Schoenflies, that can be filled in by a 3-ball, which you can check will project down to a 3-ball. OK, so unfortunately, it is not true that every 3-manifold, that the list of examples that we've seen so far exhaust the prime 3-manifolds. Okay, so that would make a nice conjecture, but it's just wrong. Okay, so I want to move toward the actual conjecture, Thurston's geometrization conjecture. And in order to do that, I need to talk about the Jacob-Shailen-Johansen decomposition. Okay, so before I say what this is, let me just change the viewpoint a little bit. So think about the prime decomposition. Right? If you take the connected sum of 2 manifolds, you start with the 2 manifolds, you remove these open balls, and you glue. Right? Well, after you're done gluing, you see that 2-sphere that you glued along. Okay? So after you do the gluing, you have a single manifold with a 2-sphere sitting in it. And you can think of reversing this connected sum operation as follows. You first identify a 2-sphere, then you cut along it. Okay, you cut open to get a manifold with 2 2-sphere boundary components. All right, and then you glue in 3 balls. That's how you reverse the connected sum operation. So essentially, the information that's in a connected sum, more generally the information that's in this prime decomposition, is really a system of disjoint embedded 2-spheres along which you could cut to get back the prime sum ends. All right? So more generally, you can imagine cutting your 3-manifold along other surfaces, not a 2-sphere, but other surfaces. And the simplest surface you can imagine cutting along would be a torus. All right? And maybe the next simplest would be a Klein bottle. So that's what the Jacob-Shailen-Johansen decomposition is about. It says that, in brief, it says that there's a canonical way, just as there's a canonical way to cut along 2 spheres, which is the prime decomposition, there's a canonical way to cut along tori. Okay? And this is the JSJ decomposition. Okay, so need a couple of definitions. So a connected embedded surface is incompressible, well, if the induced homomorphism of fundamental groups is a monomorphism. Okay, so you think of the surface N, it's a surface sitting in the 3-manifold. Saying it's incompressible means that if you have a closed loop on the surface, which can be contracted in the ambient 3-manifold, well, they can already be contracted inside the surface. Okay, what it means to be incompressible. So another definition we need is Seifert fibration. So Seifert fibration, well, before you read this, let me just say, so this is going to be a class of Seifert fibration is an example of a Seifert fibration would be a 3-manifold of the form surface cross a circle. Okay, where you have a product of a surface with a circle. A more general version would be the case where you have a 3-manifold, which is a fiber bundle over a surface where the fibers are circles. Okay, or a circle bundle. Now, a ciphered fibration is a little more general. It's kind of a fibration where you're allowed to have singularities. So to state it formally, you can say these words. So a ciphered fibration is a mapping from a three-manifold M to a surface N. So although I'm assuming M has no boundary, the target surface could have boundary. And the condition is that for each point in the target, there's a neighborhood U for which the mapping restricts to a model. Okay, so you can find a neighborhood of each point in the target so that when you look at the inverse image and you restrict your map to that, this map is equivalent to a quotient map for circle action, okay, for locally free circle action. All right, so I don't really have time to kind of dig into this. If you haven't seen this before, just think of a circle bundle or just think of a surface across a circle. Okay. And so a ciphered fibered space is a three-manifold which admits a ciphered fibration. Okay, so the JSJ decomposition, again, it's about cutting along tori and Klein bottles, says the following. So let's let M be a closed prime orientable three-manifold. So you can think of this as something you obtain by starting with a general orientable three-manifold, first performing the prime decomposition, okay? Then you plug it into this theory. So, well, then there's a canonically defined, possibly empty, disjoint collection of these NIs. These are embedded, incompressible tori and Klein bottles, such that if you have a surface S sitting in a three-manifold, which is an embedded, incompressible torus Klein bottle, then one of two possibilities occurs. Possibility A, this surface is isotopic to one of the surfaces in this family. Okay? Isotopic means homotopic through embedded surfaces. Okay? You have a one-parameter family of embedded surfaces, right? So they're not allowed to touch themselves if they move. Okay? That's possibility A. And the second possibility is that the torus is isotopic, maybe not to one of these surfaces Ni, but it's isotopic into the complement. Okay, so it's isotopic into a connected component C of the complement, where C is a ciphered fibered space. Okay, so this looks a little bit funny the first time you see it, but anyway, this is the JSJ decomposition, and with that, I can now state the geometrization conjecture. So here's Thurston's geometrization conjecture. So let X be a connected three-manifold. So a geometric structure on X is a complete finite volume Riemannian metric on X whose universal cover is isometric to one of the Thurston geometries. Okay? So you've seen the Thurston geometries before. What's a little different from what the cases we were discussing before was that before we were looking at compact manifolds. Okay? We take a compact manifold which was obtained from a model geometry by dividing out, quotienting out by a group of isometries. Okay? So here, the manifolds we're considering can be non-compact. Okay? But they can't be arbitrary non-compact guys. They have to be obtainable as quotients where the quotient has finite volume. Okay? So this finite volume is weaker than being compact. Okay, so the conjecture is that if M is a closed orientable prime three-manifold with the Jacob-Johansson decomposition given by this disjoint union of the NIs, well, then each connected component of the complement admits a geometric structure. Okay? So this is, as close as you can make the conjecture to the picture you have for surfaces. All right. So some consequences. Well, the Poincare conjecture. Let me prove something. So, condition on the geometrization conjecture. So every simply connected closed three manifold is diffeomorphic to the three-sphere. That's the Poincare conjecture. How does that follow? Well, so So suppose not. Suppose you have a three-manifold M of this sort, which is not diffeomorphic to S3, so it's non-trivial. Okay. Well, then it has a prime decomposition like this. So if you apply Van Kampen, you see that each of these prime summands are simply connected. Okay. Well, if you look at this Ni, since it's simply connected, I mean, the fundamental group is trivial, there are no incompressible tori or Klein bottles sitting at Ni. Because if there were, you'd see a copy of the fundamental group of the torus or the Klein bottle sitting inside the fundamental group of Ni, but it's trivial. Okay, so there's no Z cross Z or fundamental group of Klein bottle there. Okay? So that means that the JSJ decomposition of each Ni is trivial. Okay? And therefore, Thurston's conjecture would say that Ni itself admits a geometric structure. Okay, so to the form X, one of these Thurston geometries X modulo a group of isometries. Okay? However, the universal cover of Ni is the same as Ni since it's simply connected. Okay? So therefore, that would say that the Ni itself is diffeomorphic to a Thurston geometry. So you have a compact manifold diffeomorphic to the Thurston geometry. If you go down the list, the only one that's compact is a three-sphere. Okay? All right, well, so that felt good. Some more consequences. So the universal cover of any closed aspherical three-manifold is homeomorphic to R3. Okay, this is kind of a non-compact version of the Poincare conjecture, which had been around for a long time. I don't know exactly, probably in the 30s. You know when this is? And the word problem is solvable for any three-manifold group. So the word problem is if you're given a finitely presented group, or if you're given a finite presentation of a group, so with a bunch of generators and a bunch of relators, then you can ask the question, if you're given a word in the generating set, does it represent the identity element? Okay? So the word problem is to find an algorithm which answers that question. You feed in a word, it answers yes or no. So the reason the word problem is solvable for three-manifold groups is that, as a consequence of the geometrization conjecture, is that there's kind of you can make the algorithm fairly simple. Just as, look, you look at the word and you count how many generators are there, and then you take some double exponential function of that, and you look at that word and you look to see if there's any cancellation process with at most a double exponential number of steps in it. Okay, canceling it down to the identity. If there is, well, then it's the identity. If not, then it's not. So that's connection.
Question for the word problem to be a consequence. It looks like the input is actually that there's an algorithm for finding the geometric decomposition, not just that the theorem's true.
Well, I think you're allowed to use sort of, well, maybe it depends upon your definition of the word problem, but I would think that the...
No, but don't you have to...
The question is, what is the source of information?
I see. It's a question of whether you have the algorithm or you prove the algorithm exists.
Exactly, yeah.
Oh, okay, but in any case, what I really wanted to ask is I presume Perelman's work should give an algorithm for finding the geometric decomposition. Is it simply exponential?
Well, I'm not sure. So one interpretation of what you just said would be that there was some way of running the Ricci flow on a computer. That doesn't look. I'm not, or with error bounds or something.
Right,
but,
right.
Another might be that once you know the conjecture is true, then there's another way of estimating the coefficient in the double exponential. I would have to think about that. Okay, so now so anyway, we've seen the geometrization conjecture is, but it turns out that there's a slightly different form of the conjecture, which is equivalent to it, but which is fits more directly with the Perelman's method. So let me formulate that. Okay, so a graph manifold is a three-manifold, which can be obtained from a collection of ciphered fiber spaces by gluing boundary tori in pairs. Okay, so remember, so here you should think of something like this. So take a pair of pants. Okay, so this is a surface. This is a surface with kind of the waist, which is one boundary circle, and the cuffs. Right? You have three circle boundary components. So you cross this with a circle. Okay, so that's a three-manifold, which is a surface across a circle. Now imagine taking a bunch of those. So each of those is a three-manifold which has three boundary components. Each of them is diffeomorphic to a torus. And then you start gluing these together in pairs. So that's a graph manifold. So modulo standard arguments from three-manifold topology in order to prove the geometrization conjecture. It's enough to find a disjoint collection. So here you have some spheres, S1 through SK, and some embedded incompressible tori with the following property. Well, if you cut the manifold M open along the spheres, okay, so you kind of think of these as spheres, you're undoing connected sum operations along the two spheres. So you cut open along SIs and you fill in the boundary components with three balls. You obtain a new manifold M prime after you reverse the connected sum. Well, M prime inherits the collection of tori, and then you have to show that each connected component of the complement of this configuration of tori in M prime either admits a finite volume complete hyperbolic metric, that's a hyperbolic manifold, or that's a graph manifold. Okay? So this version says nothing about these other eight geometries. Okay? It says that you just have to find these surfaces. So after you do some cutting, the complementary pieces are either hyperbolic or graph manifold pieces. Okay? All right, so how can one try to prove a conjecture like this? Well, I mean, one of the conclusions is that you have a manifold and you have a metric on it with constant curvature. Well, so a metric with constant curvature, I mean, this is a differential equation that the metric has to satisfy. I mean, the curvature is constant. So you could think that one way of trying to produce such a metric is to start with an arbitrary Riemannian metric. I mean, every manifold has some Riemannian metric on it. And then you could try to come up with a process which kind of improves the metric and tries to make the geometry as homogeneous as possible. Tries to make the curvature more closer and closer to being constant. Okay? And, well, it turns out there is a very natural such process in continuous time. It's called the Ricci flow. Okay? So this was defined in the early 80s by Richard Hamilton. So recall that if you have a Riemannian metric G on a manifold M, well, then there's a Riemann curvature tensor at each point. So this measures the deviation of this Riemannian metric from being flat near that point. It measures the deviation from being a flat metric to the second order at that point. Okay, but this is a complicated thing. It's a tensor of rank 4. But you can kind of contract this by taking a trace, and you lose some information, but you get something simpler. You get a quadratic form, which still records some of the deviation from being flat. So this is the Ricci curvature, which I'll denote RIC. Okay? If you trace that again, you get the scalar curvature, which is the number at each point. Well, anyway, the Ricci curvature allows you to define this smoothing process or evolution. So, say a one-parameter family of Riemannian metrics, say defined where t is in some time interval, from t1 to t2. Say it's a Ricci flow. So if for all t we have the following partial differential equation. So look on the left-hand side here. So we have this one-parameter family of metrics. So if you like, you have a time-dependent metric on this manifold. So if you stand at a particular point, what is that? Well, at that point, you have a tangent space, your manifold. And the Riemannian metric is just a choice of inner product. Okay, a positive definite quadratic form on the tangent space. Well, so that inner product is changing with time. So you can take the time derivative, and that just gives you a quadratic form. Okay, so this the left-hand side, at each point in the manifold is a quadratic form. Okay, at a given moment in time. And then the right-hand side, well, we said this Ricci curvature. The Ricci curvature of the metric at that point, at that time, is also a quadratic form. So at least, this is an equation between two objects of the same type. So at least it makes sense. All right? In fact, you can, if you take a particular point in the manifold, you take the right coordinates, you can make this Ricci curvature look a lot like the Laplacian of the metric. Okay? I'm not going to attempt to make that any clearer. But essentially, from one point of view, you can rewrite this equation so it looks like the time derivative of the metric is equal to the Laplacian of the metric. In other words, it kind of looks like the heat equation. So let me ignore the fact that there's a minus sign there. So this is some sort of heat equation, heat-type equation, parabolic equation for Riemannian metric. So Hamilton introduced this in the early 80s. And he showed that if you have some initial metric, g of 0, which is a smooth metric on a compact manifold, well, then there exists a unique solution for this for short time. Okay, so they proved the short time existence theorem, existence and uniqueness. So this equation has a unique solution for short time. Well, just like in the ODE theory, if you have an existence theorem for a short time, well, and you get existence and uniqueness, well, you can prolong it onto some maximal time interval. Okay? So you have some canonically defined evolution, which is defined in some maximal time interval. Well, he went further. He showed that if this time interval is finite, so if this evolution is not defined for all time, well, then the curvature has to become unbounded as you approach this time capital T. All right? So, and for that reason, if this T is finite, it's called a blow-up time for the Ricci flow. Okay, so we have, given an arbitrary Riemannian metric on an arbitrary compact manifold is in any dimension, we have some procedure for evolving the metric and hopefully making it better. But bad things might happen. Okay? So it's 45 minutes in. I suggest maybe I take a break for...
Before everybody goes, there's been a request to change the time on Thursday to 2:30. Is this okay with everybody, or?
Thursday and Friday?
No, just Thursday.
Yeah, we don't want to change.
Yeah, is that okay? Okay, so depending on, I'm going to go up to check if the room is available. I'll tell you after the break if we really change it.
It's actually in the best.
Do you actually have any guarantee that if this thing is defined for all time, then it goes to a constant curvature metric, or can it still blow up at the infinite?
Well, it can. I mean, it's not going to converge to any. I mean, let's just converge to a flat metric. It's not going to converge to a flat metric. But it could. You have to scale. But even so. It might not converge in that sense. It sort of converges in slightly other sense. But I could get into that a little later. Because in this, so you want to see this, so one case is you have a hyperbolic manifold, but then you have other parts of the manifold which are graph look like graph manifolds. So as time goes to infinity, you get a situation where part of the manifold becomes more and more hyperbolic, part of it looks like something else, a graph manifold. So this is part of, I mean, if you localize it, this part of it
Right, yeah.
converges.
so far.
First right, first left, first right. Yeah. Internally arrested. I don't believe.
I guess so. It's weird though. Apparently. He doesn't really want to publish it.
But they're still.
Always do like those movies. I want the money like stuff that. What's weird though is like. It's just not like whoever writes it up gets the money. So that someone else can write it down.
Boiled soda water is the best.
Interested in slightly educated spectators.
Do you know DDR? Originally in the case,
Just a comment,
it's now
really during the talk. You know, there's a, do you know this David Epstein's thesis?
on the screen
It gives a slightly misleading but
you're
correct.
instructed by arrows to
Yeah,
find
say
the
that that
density
conceals
of
all the orbits are closed. Yeah. It's very difficult to be a lot of topology. And then it's false along to four. Yeah, so
Let's go somewhere.
some other, but Thurston actually supported
if you do it on your own, there's none of the social aspects of this.
Let's do a quick geometry here. See what direction it goes.
It's kind of a miracle that there's enough structure in the same world to close.
Probably. No?
So, locally free action just means, the neighborhood law. All right, let's see what happens. That's what I'm getting. So, are you going to tell us sometime before the end of Friday what the current sticking points are in declaring Perelman to be free?
I can probably comment on it. It's essentially, there's no specific thing that's really sticking point. It's in
I thought somebody told me that there was one particular estimate that in particular.
Yeah, well, he's not really, he's trying to find his own open program, so he's not really. As I said last October, yeah, he's not really. Can be viewed as a no, it did. He's probably talking about three. No, I mean, the point is the second one. But there's something back in August, towards the first head of workshop, small workshop. Without the first, which would be the bigger commercial. That's what I'm saying. Why do you want to condition the company?
No, the point is to say is to preempt criticism.
So, are there people who
Better to preempt.
believe that it's true?
Never mind. I mean, it's a compliment. Privately, I would say that, essentially everyone who's looked at it seriously is through. I think the answer is something so that publicly, the notion of things and but they emailed them, so hopefully it'll be the top side. I mean, there are a lot of social conventions. I mean, you may think I'm giving you a bullshit answer, but I think if you consider the circumstances and the way that it's written, it's really.
I asked the same question to Lisa and the answer was telling. I mean, it's not that people are going to point to Perelman's paper and say these papers contain a proof. That it will be a proof, and people have been able to reproduce it, maybe using slightly different things or filling in all their details. And a number of people have been able to kind of go through it.
People have already done that.
People have already done it.
So really the issue is.
So then why isn't there
Well, so this comes back to, I mean, I would prefer to discuss this with sort of an opportunity to discuss it for a little bit longer period because there's some subtleties in it. One can easily say something that's misconstrued.
Okay, sure.
But basically, here the paper was written in a style which is not really.
They don't actually have examples.
Style. I would characterize it as basically you can create in crucial places. But and essentially almost every place, it's a sketch which can be filled in has been filled in.
A family of time.
So it's a situation where some people write notes. This is the secondary written
Yeah,
note.
so you can get metrics that start
So
where you.
what does it mean that it's been verified? One person may fill it in one way, it's an error.
Right, yeah, the different error.
So depending upon your standard for reliability, for verification, there could be some
Squeeze and disappear.
And the $1 million hanging over it all exists that much more.
Well, but actually that's irrelevant. Because Clay is at liberty to give the prize under whatever conditions it wants to. And my understanding is that Jim Carlson told me that they would be disposed to very nice to give the prize as soon as it's weird. Well, once there's a consensus among experts, which whether or not.
Right, he froze off, right? Well, that's what I've heard. I've heard he said he doesn't want it. And they could give of course, Richard does.
Have this flow which might blow out. Okay? So you start with an arbitrary contact manifold. So there's some examples of these flows. So simplest thing you can imagine, it would be a round sphere. This is quite the simplest. You could just take a torus with a flat metric on it. Curvature zero, so it just sits there. That's the example. But more interesting would be the case where you start with a metric G0, which is the standard metric on the nth sphere. In that case, you can check the metric into IT and the original metric. Okay? But just something we'll look at function of time. So if some function of time, which you're using a multiplier, stick, if you like, certain things.
Your microphone's still on.
And that's the proof. Right. So in this case, so this function is a linearly decaying function, goes to 0, right? So the metric, which initially has curvature 1, there's a radius that's shrinking, and of course, as the size of the sphere gets smaller, the curvature gets bigger, right? And when this coefficient zeroes out, it's arrived at radius 0. The metric is degenerated and the curvature is blown up. So this has finite blow-up time. Okay. So more generally, Einstein metrics give you a very simple Ricci flow. So if the initial metric is an Einstein metric with constant c, so being Einstein with constant c just means that the Ricci curvature, that quadratic form, at each point is equal to c times the metric, that inner product. Okay. So that at each point, the Ricci curvature, that quadratic form, is equal to c times the inner product given by the metric. Well, in that case, the evolution is similar. It's just the initial metric multiplied by some affine function of time. So if c is 0, it just sits there. If c is negative, then this coefficient grows with time. So if you have a hyperbolic manifold, for instance, then it just inflates. Okay? So the curvature gets smaller and smaller. It looks flatter and flatter. And it goes to infinity. Another class of examples are products
So if the initial metric was a product metric on a product of compact manifolds, well then the Ricci flow is a product of the Ricci flows. Okay? So it respects product structure. An example to keep in mind would be the following. This is relevant for the later stuff. If you take a round metric on the two-sphere, okay, and then you cross that with the real line, so this is like a three-dimensional version of the cylinder, S2 cross R, all right, then what's going to happen to that? Well, the two-sphere factor shrinks to a point, but the R factor is flat, so nothing happens. So you have kind of a cylinder which is shrinking down in the two-sphere direction, collapsing, which is a model for a shrinking neck. Okay, so in the same paper, Hamilton proved the following amazing theorem. So if you have a three-manifold with an initial metric, it's a Riemannian metric with positive Ricci curvature. So that just means that the quadratic form, the Ricci curvature, is positive definite at each point. Okay. Well, then the Ricci flow with initial condition G0 blows up in finite time, and it converges modulo rescaling as you approach the blow-up time to a metric of constant curvature. All right, so we saw a minute ago this example. If you take the standard round metric on the three-sphere, then it blows up in finite time, and really the only thing that's happening to it is it's being rescaled. All right? So if we wanted to, we could kind of scale back, and then we would just see this metric of constant curvature sitting there. So what this theorem says is that if you have any metric with positive Ricci curvature, then it blows up in finite time, and you see asymptotically the same phenomenon at blow-up. So modulo scaling, it just asymptotically looks like a collapsing round constant curvature metric. So this is a great theorem because, in particular, it implies that the manifold itself has a metric with constant curvature on it. Okay, which I mean, it's a fantastic theorem, and this is the only proof of this theorem to date. All right, so how did he prove this? So the main tool is the maximum principle. Okay, so applied to various quantities. So let me say a little bit about this, not a lot. So we've already seen, I've already mentioned the scalar curvature and the Ricci curvature. So the Ricci curvature is just a number at each, I'm sorry, the Ricci curvature is a quadratic form on each tangent space. The scalar curvature is its trace, so just a number at each point. So the notation that I'm using following Perelman is capital R is the scalar curvature, Rm is the full curvature tensor, or Riemann, that's why they're calling it Rm, and then Ric is the Ricci curvature. So if you use the fact that the Riemannian metric is evolving in time and it satisfies this Ricci flow equation, that the time derivative of the metric is equal to minus twice the Ricci curvature. If you differentiate that equation appropriately, then what you end up with are new equations, new evolution equations, for associated curvatures. Okay? So you end up with the following PDE for the scalar curvature. So this is the time derivative of the scalar curvature equals the Laplacian of the scalar curvature. So that, if this term were here, it would look like the heat equation. Okay? But then you have this term which involves the Ricci curvature. So I should emphasize that this Laplacian is the, you should think of this, at each point, at each moment in time, you have a Riemannian metric. That Riemannian metric has a scalar curvature, which is a function on the manifold. And then you could take the Laplacian of that function on the manifold using the Laplacian of the Riemannian metric at that time. Okay, so that's what this term means there. And then, of course, you're taking the Ricci curvature at that same time. Now, this equation.
What does absolute value mean then?
It's just the norm squared. It's a quadratic form, and the Ricci curvature is a quadratic form in the tangent space. You also have this inner product sitting there. So it's really the inner product. I mean, the norm squared of that relative to the inner product that's sitting on the tangent space.
You mean the norm as an operator, or
No, it's just the sum of the squares of the matrix entries in the orthonormal basis.
So, okay, so you have a similar equation here, but this is now for the full curvature tensor. Okay, so using you can imagine, if you're not familiar with this, that there's a version of Laplacian, which is a natural operator acting on these tensor fields of type the curvature tensor. And then you have a quadratic expression here in the curvature tensor. OK, so anyway, these equations hold. And what do they imply? Well, the first equation implies that the positivity of scalar curvature is preserved by the maximum principle. And in general, the minimum value of the scalar curvature can only increase with time. So how does this work? So if you haven't seen this kind of maximum principle argument before, just think about the following. So at some given time, you have a scalar curvature function on the manifold, right? Some smooth function. Now this is a compact manifold, so it attains a minimum somewhere. Now if you look at that minimum, you know the Hessian, so the first derivative is 0 and the Hessian is non-negative. Okay? So that means the trace of the Hessian, the Laplacian, is non-negative. Right? So therefore, this term at the minimum of R is non-negative. All right, so therefore, the time derivative of the scalar curvature at the minimum is non-negative. Okay? So that it's almost a proof that the minimum can only increase with time. All right? You can turn it into a real proof without too much trouble. So that's where this statement comes from. Well, this second PDE is really a system. But Hamilton found a beautiful way of, a beautiful form of the maximum principle, which in spirit is similar to what we just did here. But it allows you to say that other quantities associated with curvature can only increase with time. Okay? And so these, by applying the maximum principle in this way, you can prove, for instance, that the positivity of Ricci curvature, that's a condition which is preserved by Ricci flow. So if you start with a metric with positive Ricci curvature, dimension 3, and then you evolve it you look at the solution to the Ricci flow equation, it will continue to have positive Ricci curvature. Okay? Which it's a statement you're going to need if you're going to try to prove the theorem that we had there before. So the next, there are a number of things one can prove using this maximum principle applied to the full curvature tensor. And one of them, which is absolutely crucial to the whole Hamilton program, which is the program that Perelman is using, is what's referred to as Hamilton-Ivy curvature pinching. Okay? So in the brief version of this says the following. So this is something that's specific to dimension 3. And the fact that there's no analog of this known in higher dimensions is a reason for thinking, I think it's unlikely that anything like this could ever be done in higher dimensions. There are other reasons for thinking that, but anyway. So dimension 3, so you start with an arbitrary metric now, no curvature condition, just an arbitrary Riemannian metric on a 3-manifold, and you start running the Ricci flow. Okay? So then the following curvature pinching condition holds. So if at some point the scalar curvature gets large, okay, well, then the minimum sectional curvature at that point is small in absolute value compared with the scalar curvature there. Okay?
Large positive or just large absolute value?
Well, because the minimum can only increase, the only way it can get large is to go plus infinity. So remember, you're in dimension 3. That any Riemannian manifold, if you choose a point, and you choose a 2-dimensional subspace of the tangent space, then there's a number associated with that, the sectional curvature. If you take a geodesic surface passing through that point with that 2-plane as its tangent plane, then the curvature of the surface is the sectional curvature. Okay? So it's the curvature associated with that kind of 2-dimensional slice there. Now at each point in your 3-manifold, you have a family of 2 planes in the tangent space. Each of them has a sectional curvature, and the assertion is that the minimum sectional curvature at this point is small in absolute value compared to the scalar curvature. So what this means is if you imagine rescaling the metric. So imagine you have a huge scalar curvature at this point. What you can do is rescale the metric to normalize that scalar curvature to 1. Okay? What happens after you do that? Well, the lower bound on the sectional curvature before scaling was small compared to the scalar curvature. And that statement will remain true after scaling. Okay? So after you scale the scalar curvature to 1, then the lower bound on sectional curvature will be almost 0. Okay? So what this says is that after you rescale to normalize the scalar curvature to 1, then you have almost non-negative curvature. Okay? And so this is an absolutely fundamental point because the geometry of manifolds with non-negative curvature is something that has been studied, well studied for decades, and these manifolds have a very restricted geometry and topology. Okay? So this fact is crucial in understanding blow-up. Okay, so more precisely, the following thing is true. There's a function phi from the reals to the reals with sublinear growth at infinity, so that if at any point the following inequality holds. So this function phi actually depends on the initial condition, okay? Which is at the moment not so important. Okay, so at each point, at a point x at time t, the lower bound on the sectional curvature is given by this function phi of the scalar curvature. So another consequence of this, it's not hard to deduce this, but another consequence is that in order to control the full norm on the curvature tensor at some point, in order to control the full norm, it's enough to just control a single number, the scalar curvature. Okay, so it's a very short argument, but to control the full curvature at a point, you just need to control the scalar curvature. It's another crucial ingredient here. Okay, so that's far I've mentioned this theorem of Hamilton, where you assume that the initial metric has non-negative curvature. And in that case, you have this blow-up in finite time and a very simple picture. I mean, the whole manifold is collapsing, and modulo rescaling converges to a metric of constant curvature. Okay? Now, if you don't assume that the initial metric has non-negative curvature, then life can get much more complicated. So if you take a metric which schematically looks like this, it's basically a round metric on a 3-sphere, another round metric on a 3-sphere, and then you glue in a metric that looks like this. So this is, of course, schematic. This is supposed to represent a 3-dimensional manifold. So this is a 3-sphere, and the region in here is supposed to be a 2-sphere crossed with an interval, say -1, 1. And then you put, on this region, you put a metric which is a product metric. Okay? Round 2-sphere cross an interval. And then you have to, interpolate in some fashion. Okay? And you can give examples like this, which are rotationally invariant. So an example like this, in this region here, what you see, if the 2-sphere factor is small, has small diameter and large curvature, what you see is something close to the example I was talking about before, of a 2-sphere across R. It's 3-dimensional cylinder. So it will tend to, because the curvature is positive and large, the radius of that 2-sphere will shrink fast. And the more it shrinks, the larger the curvature gets. So the faster the radius shrinks. So this guy is going to want to pinch off. Now over here, the curvature is moderate. So you might expect that really nothing much is happening. Okay? In fact, this is the case, although justifying that statement is more difficult than you might think. So what happens with such an initial condition is that something happens here. The curvature blows up locally here. But at that blow-up time, nothing much has happened over here. Okay, so as you approach the blow-up time, the geometry is converging. You get some sort of limiting geometry over here, which you can imagine is still fairly close to the constant curvature metric you started with. Whereas here, it's going to hell. So this is very different from the picture that we saw before with positive Ricci curvature, where when the metric goes singular, it goes singular everywhere at once. And that's because the whole manifold is assuming some canonical shape. Okay? So you can have pictures like this. Now, if you try to, what we're discussing here is some nonlinear parabolic system. And we're trying to understand what can happen when it goes singular. So as kind of a mental exercise, you can try to concoct solutions or approximate solutions which blow up to get some idea about how things might go haywire. All right? And if you do that, the only thing that you can really come up with as convincing pictures are things like neck pinches and slight variances. Okay? So you could also imagine a picture like this where you have kind of a neck pinching. So So it shrinks down, but then instead of opening up on the other side, it might have a cap. It might get capped off like this. So, yeah. Or you could imagine that somehow, instead of collapsing to a metric with constant curvature, you could have a situation like this. You could have a three-manifold, which is a two-sphere, across a circle. Okay? So here you have a cross-section, which is a two-sphere, and then that's product of that with a two-sphere. And something like this could collapse everywhere at once. But it would have neck-like geometry as it collapses. So essentially, these are the only pictures people could come up with. And so it became natural, or Hamilton at this point was probably the only person thinking about this. So when you look at this picture, you think, well, maybe what we should do is just run the Ricci flow and let the singularity form, and then assert, well, the singularity, only thing the singularity can be is a neck forming, essentially. And then what we can do is to think, well, this neck has some cross-sectional two-sphere in it. We cut out the neck and glue in caps like this, and we've topologically undone a connected sum. Okay? And now we have a new metric, which is no longer singular, and we can restart the Ricci flow. So this was the idea, okay, which, you know, at first sight sounds pretty wild. So this is the outline. So Perelman's argument for geometrization. So in phase one, so I call this phase one. You're concerned with the structure of finite time singularities. Okay. So you start with an arbitrary metric on your three-manifold, and you run the Ricci flow up to the first blow-up time. Okay. And then what you want to do is to do this kind of by-hand surgery operation where you reverse a connected sum. Now, if you think about it, in order to do this, you're going to have to identify a part of the manifold which looks suitable for performing the surgery. Okay? And that, in order for this to make any sense, you have to, in some way, show that when a blow-up occurs, there will be such a part of the manifold. Okay? So the strategy is to show that all the singularities have a standard form. So you give it basically a description of the whole part of the manifold where the curvature is large. Okay? And this, when the smoke is cleared, what it says is that wherever the scalar curvature is large, you have to see a picture that looks locally like, you know, a neck like this or a neck like that, which might be capped off. You might see something like this. Okay? Or you might see something like a blob, which is like one of these spherical space forms, which is going to collapse after a moment. Okay. Anyway, so that's the first part of the program. So to try to identify the geometry when a blow-up occurs. Okay, so phase two. Here we assume phase one is complete, so we know what's happening at when the flow goes singular. So you can stop the Ricci flow either at the singular time or maybe slightly before, and you'll see these places where you want to perform the surgery. Okay? You'll identify them by phase one. And so you perform that surgery. So you cut out part of the manifold, and you glue in these caps. And you have to do it. You can't do it in a haphazard fashion. You have to do it respecting the geometry to a significant extent, but that's the idea. Then you restart the flow. Well, so you restarted the flow. Maybe it goes singular again. All right, so you stop it, you cut it out, etc. So you have a sequence of times, the surgery times, and the main content in phase two is that this flow with surgery can be defined for all time. So the problem here is that a priori, if you do this process incorrectly, you could have a sequence of surgery times which accumulate. Okay, you flow for a little while, it goes singular. Do surgery, flow again, but for less time, it goes singular. Okay, etc. And then if you had a pileup of these surgery times, then it would be unclear how to proceed, and it would essentially kill the whole program. All right. So excluding that, Showing that you can run this process for all time, that's phase 2.
So there's no claim in phase 2 that there's only finitely many surgeries?
That's right. There's no such claim. Okay, in phase 3, so that studies the long-time behavior of the flow with surgery.
You're not claiming that there's...
Is it flow with, so the flow with surgery, is that with scaling? Because, so if you started with just a sphere, I mean, then it would contract down. So are you using with scaling? Because otherwise you...
Well, what you do, the surgery process there would be, at the blow-up time, you just throw the manifold away.
Okay.
Okay? So I should clarify and say, saying the flow of surgery can be extended for all time, that includes the possibility that you're flowing the empty set. Okay? Which turns out to be a favorable case.
From a PDE point of view, so you get to the point where you're going to cut. Okay, so what you're going to do is you're going to leave on that side the PDE as it was, basically the metric there is not going to change, and you're going to change it a tiny bit here. And there's something to the effect that this thing will continue to behave well and it's not too far. I mean, what if you had cut a little bit later, then you will have cut something else. So do the two things go to the same outcome afterwards?
So that's an interesting question. So what happens, so when you do the surgery process, it's not canonical. So there's a certain amount of, there's some parameters in play, which to some extent are at your disposal. One of them has to do with the size of the neck region where you perform the cut. Okay? So this discussion does not address, he does not address questions like, so how does the process depend on those choices? He does, the only thing that he speaks to is the question, can you choose those parameters in such a way that the process will be defined for all time?
My question is the PDE posed in the following sense, you can cut here and then cut a little bit later, and then you flow these two different cuts. Are they going to flow to the same thing? I mean, as he proved, or do they be flow into different things?
Well, it depends upon how you're quantifying this and whether you're asking whether the statement is true beyond subsequent surgeries. So if you do these two surgeries and then you flow, okay, and you just flow over a time interval during which there are no other surgeries, then you're essentially talking about unique continuous dependence on initial conditions for Ricci flow. If you want to make a similar statement where you permit surgeries during a subsequent time interval, then it even becomes a question what you mean by having two nearby Ricci flows with surgery. So you have to even figure out what the correct topology is. So there's actually, and I'll discuss this later, there's some questions which I think are very interesting, at least from an analytic point of view. Their topological implications are, I don't see any value for them topologically, but I think they're very interesting analytically having to do with this kind of thing.
So you're not claiming finitely many surgeries, but is it true that in the end there will be?
I'll get to that in a sec, the next slide, but let me just say what happens in phase 3, okay? So in phase 3, we assume that we have this surgery flow defined for all time, okay? And so, which might be empty, might not. But if it's not empty, then as time goes to infinity, what you see is a collection of hyperbolic manifolds glued along incompressible tori to graph manifold. So if you have a hyperbolic 3-manifold with finite volume, non-compact, then what it looks like is something like this. So this is a classical fact. It has ends, and each end will be diffeomorphic. The end looks like this. It's diffeomorphic to a torus across the non-negative reals. Okay? And metrically, it looks like a product where the torus factor is warped. It shrinks exponentially as you move out the end. So, so if you have such, say, two such manifolds, you can imagine chopping off this end. Usually it's called a cusp. You get a manifold with a torus boundary. Okay, and you take another such guy, chop it off, and glue along the torus. Okay, and you can also glue. You can chop off and maybe glue to a graph manifold as well. So these are the kinds of pictures that you might imagine occurring in phase 3.
Bruce, can I ask you another question about phase 1? So was phase 1 kind of completely done before he started?
No.
So the pinching theorem that you had before only told you that one direction was coming flat and the other, and then one, you couldn't prove that the two other curvatures were basically comparable. That's why you didn't know that these were.
Well, there are different ways of saying it. I mean, this pinching result, this Hamiltonian pinching result, is a statement about the curvature at a single point. What's needed to run this surgery argument is a local description. So it's not a single point, it's actually in a neighborhood. So, I mean, there's a big step from, second order. So, all right, so this, I mean, I call this Perelman's argument for geometrization. I should emphasize that this, this outline is similar to one proposed by Hamilton long ago. Okay, so Hamilton had some sort of three-phase program, but actually there are important differences even between the outlines. Okay, so I would say maybe the main differences are that Perelman does not show that only finitely many surgeries occur, whereas Hamilton had wanted to show or conjectured that if you do surgery correctly, then only finitely many surgeries occur. And moreover, in phase 3, he's essentially conjecturing that after the last surgery, if you look at the evolution, then the curvature remains bounded if you make an appropriate scaling. Okay? So, and the bound he was envisioning was a bound on the norm of the curvature tensor, which you can think of as a bound from below on the sectional curvature and a bound from above on the sectional curvature, and eigenvalues, if you like. Whereas Perelman does not prove that. What he gets is spaces which have a lower curvature bound, not a lower and an upper curvature bound. Technically, this is a very different story. So Hamilton's program is still conjectural. So there's been essentially no progress on trying to prove that, even using Perelman's methods.
So I don't understand that second difference. If the curvature went to infinity positively after you were done with all the surgeries, wouldn't you come up to a it's a question of finite versus infinite time? Or, I mean, I'm wondering why, with the curvature increasing at some point, you don't come to another neck pinch.
This is, okay, so I should say, the thing that Hamilton's asserting here is sort of with the appropriate scaling. So you scale to normalize the volume to be 1. Okay? So
But I'm trying to understand the possibility that Perelman's approach allows. It says that when you're all done with these surgeries, it still may be that some sectional curvature is going to infinity with time.
How do you talk about all done with surgeries if
in Perelman's case,
right?
In Perelman's case, there won't necessarily be. A priori, there could be an infinite sequence of surgery times. It's discrete, so the sequence of surgery times runs out to infinity.
So
how do you get geometrization refer to then? What does phase 3 refer to?
So it says that for large time, what you see, you have a manifold each time. I mean, surgery can change the manifold, but it's not hard to see that after finitely many surgeries, the topology doesn't change. All the surgeries are doing something that's topologically trivial, like pinching off the sphere. But
so you get to geometrization before going to infinite time.
Well, almost. Yeah.
And how do you identify these as hyperbolic manifolds if the metrics are not converging to hyperbolic metrics?
Well, but you see, it depends upon what you mean by convergence. So we can get pointed convergence, hyperbolic metrics. So you can find, if you flow to infinity, you can find a sequence of points in the time slices, so that if you look at the time slices with those points, you sort of focus your attention near these particular reference points, then the metrics will look like they're converging to hyperbolic metrics. But so what's happening is there could be some other crap out here. I mean, a graph manifold, but it's sort of the graph manifold pieces are moving further and further away from the hyperbolic sort of core, the cores of hyperbolic pieces.
But these additional surgeries, they're happening away from the core of the hyperbolic pieces. They're happening either near the cusps or in the graph part.
Right. Exactly.
And the graph part is where the positive curvature could be coming from.
So this was supposed to be the first half hour of my talk. Okay, so yeah, so I think I may as well stop on time. So let me just put one more slide here. So the remainder of the lecture is going to discuss some highlights of this argument. So we'll start with phase one. And the strategy there is to show that if you look at a point in space-time where the curvature is large, so a point where the scalar curvature is large, well, then we want to say that the Ricci flow looks like a model flow. I haven't said what a model flow is yet, but I will in due course. These are a special class of flows. And this effectively reduces the problem of understanding the high curvature part of the flow to understanding these model flows. Okay? So really, I mean, there's a long tradition of theorems or proofs in PDE which have the following rough outline. So you have some evolution equation, or maybe just a sequence of solutions to a PDE, and they're not converging to anything. Okay? However, you can identify a quantity which is blowing up to infinity, some sort of energy density, maybe some pointwise energy, whatever, which is blowing up to infinity. Okay, and this is the reason it's not converging. So what you do is you rescale. Okay, in order to do this, your equation has to have the right characteristic for this scaling process to be useful. But in this case, it does. So you rescale to make this quantity, which is blowing up, stay under control. Okay? We already saw this in the example of a collapsing sphere. Okay? So after you rescale to keep this quantity under control, you want to assert that the sequence of solutions converges to something. Okay? And so at this stage, you invoke some sort of compactness. There will be some sort of functional analysis type compactness result, maybe. In this case, it's a little more concrete than that. And then you get some sort of limit. All right? And the idea is that if you have an equation like the Ricci flow, which has a sort of heat type character to it, which is trying to smooth things out, then when you magnify things, when you rescale things and pass the limit, you get a very nice object. Okay, so things get better on a smaller scale, and in other words, you're sort of sucked into these pictures where you see a neck or some very special geometry. Okay? So that's the strategy for dealing with